Welcome back. So, this is lecture 52 in this course on Bayesian modeling. Topic of this lecture is Bayes factor. In the previous few lectures, we discussed one of the method for model comparison, which is cross validation. We basically first discussed the idea behind model comparison, that what exactly we want to evaluate when we want to evaluate how good is a model, right? So, how do we evaluate whether a model is a good model or a bad model? Well, we evaluate it by measuring the predictive accuracy of the model given some future data. So, how well or how accurately the model can predict future data. Okay. So, that is how we measure whether a model is a good model or bad model. But this measure is never absolute. We need to compare it with some other competing model, right. So, we can always do this model comparison. We can compare two models in terms of their predictive accuracy. Okay. So, one of the method of measuring relative predictive accuracy of two models is cross validation, right. So, in cross validation you do not require future data, you can split the same data into multiple portions and train the model on one portion and test its accuracy on the remaining portion, right. So, this whole approach of cross validation where we use the measure called expected log predictive density, it uses posterior predictions of the model. So, it checks whether posterior predictions of the model are able to capture the future data. Okay. So, that was the whole idea behind cross validation. Now, there is another method of quantifying evidence for a model, okay, and that method is called Bayes factor analysis. Okay. Let us go into this, that what is Bayes factor and how we can use it for model comparison and hypothesis testing. So, if you remember, there was one term that we have left during parameter estimation, but it was useful in Bayes theorem. The term was the denominator called marginal likelihood. Okay. It was marginal likelihood. What was marginal likelihood? So, suppose you want to estimate posterior distribution of a parameter theta given some data y, then this posterior distribution is given by likelihood of the parameter theta, prior distribution of theta divided by integration of likelihood into prior with respect to theta. This term, integration of likelihood into prior with respect to theta, this is called marginal likelihood, ML. Okay. Now, why this is relevant here, I will tell you in a while, right. By the way, there is another way of writing marginal likelihood, or in fact another way of writing this Bayes theorem, P theta given y likelihood of, another way was this, if you remember, conditional probability of y given theta, P of theta divided by total probability of y, right. So, marginal likelihood is actually total probability of y by marginalizing out this parameter theta, right. This is another way of writing the same thing. Okay. So, why this is relevant? So, let us think about two models, model M1 and model M2. Let us say you have two models, M1 and M2, and you have single data, let us say y, which each of these models want to explain. Our goal is to select model M1 or model M2 based on whichever is better at explaining this data y, whether M1 is better at explaining data y, whether M2 is better at explaining this data y. Okay. That is our goal. So, how do we do that? Can we think of probability of choosing model M1 given data y, probability of model M1 given data y. So, how likely is model M1 given this observed data y. Okay. This is what we are interested in. Okay. And we can compare it with probability of choosing M2 given data y. So, how likely is model M2 given this data? Okay. So, what would be this based on Bayes theorem, probability of M1 given y? Well, this would be given by probability of y given M1 into prior probability of M1 divided by, let us say, summations probability of y given Mi into probability of Mi from I1 to n. Okay. So, this is how probability of choosing model M1 would look like given data y. Okay. What are these? Mi, M1, M2, M3, basically you are doing this summation across all possible models that can generate this data. Okay. So, let us say there are 10,000 possible candidate models. So, you are summing this up across all those 10,000 models, right. So, given a space of huge number of models, how likely that you can generate this data y. Okay. So, this is overall total probability of generating this data y given all possible models. That is what it says, the denominator term. But what is the numerator term? What is P y given M1? It tells you the likelihood, how likely is that data y can be generated by this model M1. Okay. So, this is like total probability of y being generated by model M1. Okay. What is another term? P of M1? This is prior probability of this model M1. So, this is your prior belief. Do you believe that model M1, or let us say if you have some bias that you are always going to select model M1 regardless of whatever data you have. So, this is before seeing the data. So, how much is your prior belief or your prior bias for model M1? Okay. This we can ignore for now, but this is what the term that is interesting for us. We will focus on this. This is probability of y given M1. Okay. This probability is actually with what probability this data y is generated by model M1. Okay. So, what is this probability? Can you calculate this? This is different from this one. This probability is different. This probability is telling you how likely is a model M1 if data y is given. Okay. But this is how likely that a particular data y will be generated by model M1. So, in a way you are saying that model M1 can generate different kinds of data set, but how likely it is to generate exactly this observed data y. Okay. In this case, given data y, you can select either model M1, M2, M3, there is a huge range of models you can select, then how likely it is that you will select model M1. So, these are different probabilities. So, what is probability of y given M1? Interestingly, if you notice the marginal likelihood, so marginal likelihood is giving you probability of this data y or the likelihood of this data y given all possible values of the parameter in a particular model. Okay. So, in a way this is giving you likelihood or probability of generating this data y given the entire parameter space of this model M1. Okay. So, this is giving you probability of generating this data y given model M1. So, you can think of this probability of y given M1 as integration of, let us say, P y given theta prior density of theta d theta. If you marginalize out theta, this will give you probability of y given M1, where theta is a parameter. So, such that yi comes from M1 theta. Theta is a parameter of the model M1. Okay. So, basically this term probability of y given M1 is the marginal likelihood of model M1. Okay. So, now you can rewrite probability of choosing model M1 given some data y is given by probability of y given M1 into probability of M1 divided by summation of probability of y given Mi into prior probability of model Mi, I equals to 1 to n. You can rewrite it in such a way that this thing is marginal likelihood of model M1. Okay. So, probability of M1 given y is equals to marginal likelihood of model M1 into prior probability of model M1 divided by summation of marginal likelihood of model Mi into prior probability of model Mi. Okay. So, this is for model 1. We do the same thing for model 2, M2y, marginal likelihood of model M2, prior probability of model M2, summation marginal likelihood of Mi into prior probability of Mi. Notice that the denominator term is same for model M1 as well as model M2, because what denominator term is telling you how likely is it to generate the data y given all possible models. Okay. So, let us say you have all possible 10,000 models, how likely that you would generate this data y given all the models, right. That is what the denominator is telling you, right. So, this is why it is same for model 1 and model 2, right, because it is a constant term regardless of whatever model you choose, right. So, in these equations, this term is marginal likelihood of model 1, this term is prior probability of model 1. What is this term? This is posterior probability of model 1 given the data, right. Similarly, here this is posterior probability of model M2 given the data. What if I take ratio, what if I divide equation 1 by equation 2, okay, on both right hand side and left hand side, then I will get probability of M1 given y divided by probability of M2 given y, and here the denominator will cancel out because it is same for both the models. So, what you will be left with, marginal likelihood of model 1 divided by marginal likelihood of model 2 into prior probability of model 1 divided by prior probability of model 2. This is called posterior odds, because this is the ratio of posterior probabilities of model M1 and model M2 given the data. This is the ratio. So, this is actually posterior odds of model M1 with respect to model M2. This is the ratio of marginal likelihoods, and this is the ratio of prior odds, right. Now, the posterior odds basically gives you relative evidence for model M1 compared to model M2, right. Well, of course, in practice, we often assume that we do not have any prior bias in favor of any model M1 or model M2. So, we assume that this ratio is equal to 1. So, we can ignore this term, assuming that this is equal to 1. We have equal prior for M1 and M2, equal prior probability for M1 and M2. So, this is the only thing that matters, ratio of marginal likelihood of model M1 compared to model M2. So, if this ratio is greater than 1, that means model M1 is better at explaining the data than model M2. If this ratio is less than 1, then model M1 is poorer than model M2 at explaining the data, right. This ratio of marginal likelihoods is called Bayes factor. Okay. Ratio of marginal likelihood of two models is called the Bayes factor. Okay. And that is what we use to quantify evidence for a model compared to another model. Okay. So, let us say you have some model M1 such that the model M1 assumes yi comes from f of theta, where theta has some prior. Model M2 assumes that yi comes from g of phi, where phi has some prior p of phi. right. Now, Bayes factor in favor of model 1. In favor of model M1 would look like this. You can write it like this, BF12. So, Bayes factor in favor of model 1 would be marginal likelihood of model M1 divided by marginal likelihood of model M2. What would be marginal likelihood of model M1? So, it would be likelihood of theta given y p of theta d theta. What would be marginal likelihood of model M2? It would be likelihood of phi given y prior density of phi into d phi. So, if you can calculate these marginal likelihood, you take their ratio and this will give you Bayes factor. And how would you interpret Bayes factor? So, if let us say Bayes factor is greater than 1, then that means evidence, or let us say model 1 is more likely, that much times more likely than model M2. So, evidence in favor of M1, and if BF12 is less than 1, then evidence in favor of model M2. Okay. But there are some conventions. So, for example, if Bayes factor value is let us say between 1 and 3, okay, then you cannot say that there is reliable evidence. You can say there is some anecdotal evidence in favor of M1. If it is between let us say 3 and 7, you can say there is moderate evidence, moderate or weak evidence in favor of M1. If it is let us say 7 to 10, okay, then, or let us say greater than 7, okay, then you can say there is a strong evidence in favor of M1. Okay, if it is greater than 10, strong evidence, like that, right? So, there is some convention. So, let us say if it is close to 1, then you would say there is anecdotal evidence that you cannot really trust this evidence. If it is let us say somewhere between 3 and 10, you can say there is weak evidence. If it is greater than 10, you can say there is strong evidence, like that. Yeah. But crucially, to calculate Bayes factor, you need to calculate marginal likelihood for each model. And we have been over this problem in the past, that it is difficult to calculate this marginal likelihood. It is difficult to do the integration when you do not have a conjugate prior, and that would be the case for most models, for kind of models that we use, right. So, how would you calculate marginal likelihood of a model in order to calculate Bayes factors? Well, you need some algorithm, right. So, for example, one of the algorithms that we saw was basically you need Monte Carlo integration here, right. Monte Carlo integration. How does Monte Carlo integration works? So, suppose you want to calculate this marginal likelihood, likelihood of theta given y, p of theta d theta. You want to calculate this integral. Now, you cannot solve this analytically, so we will use some computational method. So, actually what you can do, let us say you draw some values of theta, let us say theta I, from some density, from some let us say importance density g of theta. Okay. Now, conditional on each theta I, if you calculate the likelihood prior and divide it by this density g of theta I, because theta I would have all values, because if you are taking multiple values of theta I from g of theta, it would have its inherent distribution. We want to take out that bias. Okay. So, likelihood into prior divided by g of theta and its summation, it's actually average. So, if you are taking n samples, then take its average. So, if you take average of likelihood into prior divided by g of theta, where theta is are coming from g of theta, right. Okay. So, if you do this, then this would be a good approximation of your marginal likelihood if this n is large enough. So, let us say if you take 10,000, 1 lakh or millions of observations, millions of such samples, right, then the marginal likelihood can be approximated with good approximation. Right. This is how Monte Carlo integration works. Right. You can use it and try and see what happens. Right. But there are more sophisticated algorithms, for example, bridge sampling. So, you will find it in both Python and R. So, this is a package that you can use to estimate Bayes factors and marginal likelihoods. So, this is a brief intro on Bayes factors. So, just to recap, this is another way of evaluating a model against another model. The method is this, that we can calculate the posterior probability of a model given the data. We can calculate how likely is a model given the data. So, how likely you are to choose a particular model given the data, and that will be given by probability of data given that particular model. But this probability of data given a particular model is same as your marginal likelihood. This is basically total probability of obtaining this data given the entire parameter space of that model, given all possible values of the parameters in that model, right. So, this is basically P of y, same as your marginal likelihood, right. So, essentially the ratio of posterior probabilities of two models becomes the ratio of marginal likelihoods under the assumption that there is no prior bias for any of the model. Okay. So, this ratio of marginal likelihoods is called the Bayes factor. So, Bayes factor actually gives you how likely is model M1 over model M2 given the data. So, it gives you relative evidence for model M1 compared to model M2. Okay. So, that is what we are going to quantify. So, how likely is model M1 over model M2 given the data, right. So, if Bayes factor is greater than 1, we can say there is more evidence in favor of model M1 compared to M2. If Bayes factor is less than 1, then there is evidence in favor of model M2 over model M1 given the data y. Okay. But in order to calculate these marginal likelihoods, you might need some computational method like Monte Carlo integration, because you won't be able to solve it using analytical methods. So, in the next lecture, we will take some simple example and we will estimate evidence in favor of a model given another model. Okay. But there is one important point missing from this whole discussion, which is that what is the difference between Bayes factor and cross validation, right. So, both are methods of model comparison, but what is the difference between the two, and in what situation it is better to use one method over the another. Okay. So, that is a point we will discuss in next lecture or after that. Okay. So, difference between cross validation and Bayes factor. Okay. All right, I will stop here for this lecture. In the next lecture, we will implement Bayes factor analysis in R. Okay. All right. Thank you very much.